We are here to study asteroids, which are small, mostly rocky bodies in the solar system. The main body of asteroids lie between the orbits of Mars and Jupiter. The ones we're studying are slightly further out, at Jupiter's distance from the Sun. That's about 5 times as far as the Earth. Asteroids are important because they are small chunks of rock that are left over from the formation of the solar system. They have banged into each other a lot, broken up. We think most of them are probably not solid bodies, but fractured pieces of rock. And they can tell us a lot about what things were like in the early solar system.
We're interested in studying the Jupiter Trojans, called the Jovian Trojans, because they might be different than the main belt asteroids that lie between Mars and Jupiter. They might be more icy in nature than the rocky ones found closer in towards the Sun.
The way we're studying them is to measure the way they reflect light. An asteroid turns, and so think about, if I were giving a talk on this, I'd probably have a potato on a stick. And think about that, turning that stick with the potato. It reflects sunlight, and when the broad side of the potato faces you, you get more light. When the end faces you, you get less light. So if we map out the brightness, we would get 2 bright spots and then 2 dimmer spots. And that tells us how fast the asteroid is turning, the length of its day. Think about it that way. And this tells us something about the properties of the asteroids. If we look at a whole lot of asteroids, hundreds to thousands of them, in the main belt of asteroids, their rotational properties behave in a certain way. The Trojans are a little bit different in that what we're finding is some that are really, really slowly rotating. We're also looking to see if there are some that are spinning really fast. So far, we haven't found those.
And if a fast spinning Trojan, if it is indeed icy in nature, would fly apart if it was spinning too fast. We know this is the case of the asteroids that are near Earth, the near-Earth asteroids, in that there's a what's called a spin barrier, meaning that if they're spun up faster than about 2.2 hours, the materials start shedding off the asteroid and they form a moon, or they just simply fall apart. That tells us a lot about how dense they are and what they're made of. But we think the Jupiter Trojans are somewhat different in that the iciness of them will cause them to fall apart, if they're spinning about one rotation every 6 hours is what I'm trying to say.
Yeah, you could think about the spin barrier by thinking about those amusement park rides. The kind of that's a big wheel, and you get on, and you're standing there, and as it spins faster and faster, the floor suddenly falls out from under you. That would be the same forces that would be acting at the surface of the asteroid right as it breaks apart.
And this is something important to the formation of the solar system. It's an open question as to how the solar system got to where it is today. How its state got to where it is. Why do we have Jupiter where it is? Why is Saturn where it is? Why are the other planets where they exist today? And there's some theoretical models that show us how we could have gotten to this arrangement of our solar system, and those models actually predict that the Trojans will be where they are and made up of certain types of material. So we're trying to test that theory to assist in modeling the evolution of the solar system.
Yeah, and according to this theory, the Trojans would be very closely related to comets, which are found generally either much further out in something called the Kuiper Belt that starts out around where Pluto is, or the Oort cloud, which surrounds the solar system. So there are many lines of evidence that point to a similarity between comets and the Trojan asteroids. They look similar when we can see with their surfaces. how they reflect light. But what we're trying to test is whether the composition as we can see it through their rotation is similar.
Asteroids that form further out in the solar system tend to be icy in nature, and asteroids that form closer in towards the sun tend to be rocky in nature. Back when telescopes were first invented and people started taking photographs of asteroids with photographic film, they were very hard to find because they looked just like stars in the background. They're points of light, and the only way you knew that you had the asteroid is if it moved over time by taking two pictures and comparing them side by side. You're looking for the dot that moved. Now, with modern computers, it's a lot easier. Functionally, what we do is just load the image, the picture of the asteroid, up into our computers, and in the process of loading them into the software identifies where the asteroid is and draws a circle around it. All this just takes just a few seconds. When we're sitting at the telescope, we usually have two computer screens up. One shows a map of the sky where the telescope is pointed, and one shows the pictures that you're taking. And conveniently, your map of the sky has an arrow pointed at the asteroid, so you know exactly which one that you're interested in.
If we don't have that map of the sky, we can always just take two pictures, maybe 5 minutes apart, and you'll see that the stars, of course, stay the same because they're so far away, and something that's closer to us, like an asteroid, will appear to jump from one picture to the other. So this technique is called blinking, and we can go back and forth if we need to. Now with the telescopes here, the professional telescopes on the mountain, we don't have to go hunting and searching for the asteroid. They generally point right to where it is, so it's generally very easy to